Hey everyone, it's Becca. Welcome back to Ask Becca About Space. I hope you guys enjoyed your Easter weekend. I did, even though I'm kind of stuck by myself in another country from my family. We still had a bunch of Zoom meetings and house party meetings and got to play some games and hang out with each other a little bit. So I hope that even if you're away from your family, you still had some nice kind of family and friends time over the holiday. Okay, so today I'm pumped because, as per usual, I am going to start addressing some questions from my friend Lillian. Lillian has submitted a bunch of questions and I am here for it. So let's just dive right in because I'm excited to get to it. Okay, so Lillian's first question is, can there be more than one star per solar system? Great question, Lillian. The short answer is yes. But first, I want to talk to you a little bit about how we observe planets to move around stars. Okay, so there was, back in the 17th century, a mathematician and astronomer, and actually he was also an astrologer, called Johannes Kepler. And from Johannes Kepler, we have what we call Kepler's laws of planetary motion. Okay, and these laws kind of dictate the way by which we understand planets moving around a star, right? Or essentially anything in orbit around anything, right? So he has three laws of planetary motion. The first one is basically that when a body is in orbit around another body, that orbit is shaped like an ellipse. Okay, so not necessarily a perfect circle, but stretched out a little bit like an oval. Okay, the second law is that the planet has to sweep out equal areas in equal times. And basically, what that means is that if you are a little bit closer to your kind of home star in your orbit, then you need to move a little bit faster to make sure you cover the same amount of ground as you do when you're a little bit farther away from the star. Okay. More or less, a lot of the planets that we see in our own solar system, with the exception of Pluto, it's a dwarf planet anyway, but with the exception of Pluto, we have very close to circular orbits. So when we're a little bit closer to the sun, a little bit farther away, we don't necessarily feel that here on Earth. We wouldn't anyway, because in our reference frame, standing on Earth, we're at rest. But when we're a little bit closer to the sun, we are moving a little bit faster to get around that orbit a little bit quicker, to sweep out that same amount of area in that same amount of time. But when we're farther away from the sun, we kind of take our time a little bit more than usual. This is more obvious in things like comets that have highly eccentric orbits. Eccentric meaning that oval is stretched out a lot. Okay, so when comets are super, super far away from the sun, they're not moving that fast because they don't need to. They're sweeping out a very large area just by being far away from the sun. But when they're close to the sun and they don't have that much distance between them and the sun, they move quite quickly to sweep out that same amount of area in the same amount of time. That's Kepler's second law of planetary motion. Kepler's third law relates the time it takes to orbit around that star to the distance between that star and that body. In particular, what we call the semi-major axis, which is the longer distance between the star and that body relative to the shorter distance. Okay, again, that's a little bit more obvious for comets. Their semi-major axis, when they're kind of out in the Oort cloud, is quite a bit longer than their semi-minor axis when they're quite close to the sun. Okay, and basically the third law says that the semi-major axis length is related to the time it takes to complete a full orbit. Okay, so we have these laws of planetary motion that were set forth by Johannes Kepler in the 17th century, and we've pretty much leaned on those laws for up until now. Because what we've been observing, what we've been able to observe up until now-ish, is one star systems, because that's what we have, that's what we know. The closest planets to us are, as far as we know, orbiting around one star. And because of that, we have a relatively simple picture of what those orbits look like, and they fit mathematically into the model created by Johannes Kepler. Okay, fast forward to now, and we have a mission, a NASA mission, a satellite named after Johannes Kepler. So it's called the Kepler Mission, appropriately because it is looking for planets outside of our solar system. Okay, so the Kepler mission is a piece of spacecraft that is looking at one particular tiny rectangle of the sky, and it is staring at that until it sees anything change. That's kind of a weird thing, right? Because obviously, if you stare at something in space long enough, it's going to change. There are things happening in space all the time. But what it's fine-tuned to look for is changes, in particular, in starlight. And more specifically than that, it's looking for changes in starlight that make the star systematically dim periodically and in a constrained period, in a period of time that is repetitive and that is measurable and that we can see. Okay, now the reason we're doing that, and the reason Kepler is doing that and was designed to look for changes in starlight, is because planets are generally too small and too dim for us to observe directly if they're not inside our solar system, right? Because if you've got a planet that's really far away and it's not giving off any of its own light, it's only able to perhaps reflect some of its home star's light, but that's not really enough to make it all the way to our eyes here on Earth, right? So if you're looking for those things, but they're not really giving off any light, then you have to find another clever way to find them. And what happens when a planet comes in front of a star is just the fact that this kind of point source is in front of this light source. It dims that light source just a little bit as it passes by. And when it comes back around on its next orbit, it will do the same thing. It will dim that starlight just a little bit, right? So when it does that, it does a very specific and measurable thing to the light coming from the star. If I were to measure the light coming from the star, it's supposed to be relatively constant if the star is a stable star. The starlight is relatively constant, but when that planet comes, it dips a little bit into kind of a U shape. And as the planet leaves the star's face, it comes back up to that constant. So what Kepler is measuring is the light curves, that's what we call them, the light curves, from those stars. And if the light curve tells us, oh, that looks like there's something moving in front of that face, let's keep looking at that star. And if we're able to see that happen again, and see that happen again, and see that, okay, this is happening periodically, we can probably convince ourselves then that something is moving in front of that star every so often at the same time every time. That is indicative, or that tells us that there's a planet moving in front of that star's face. So Kepler was designed to stare at a region of the sky that is kind of looking straight into one of the arms of our Milky Way. So the density, or the amount of stars per this kind of surface area, or this volume, is quite high. So there's a higher chance of finding planets orbiting stars with this light curve method. An extra fun thing that has been discovered is that some of these planets are orbiting multi-star systems. Okay, so we have planets in orbit around binary stars, which means two stars. It's also possible that there are planets orbiting ternary or trinary star systems, which is 3 stars. We have quaternary star systems, 4. And then all the way up to, I think we've got confirmed 8 star systems, which is crazy. And then kind of apart from that, we have star clusters, but that's a little bit of a different theory there, because those are either very young stars or very, very old stars. And up until this point, I don't know of any planets hanging out in star clusters as much. It's possible that planets are forming in young star clusters, but I don't know anything specific about that. However, there have been detected planets orbiting around these multi-star systems. That's super cool. Here's the problem. Kepler's laws of motion work very, very well when you have one star in the center of mass, basically, of the solar system, okay? Or the stellar system, whatever you want to call it, okay? When we observe a planet orbiting a system that has kind of a more spread out center of mass, either because the two stars that it's orbiting are very equal in mass, or because one is huge and one is small but still bigger than the planet. That messes up the kind of local gravity of the system, right? It messes up the distribution of the center of mass of the system. And now we don't really have a mathematical model that is able to align exactly with Kepler's laws. And so what happens is the orbital dynamics, or the way by which we can mathematically and physically and intuitively describe the way that those planets are moving around that multi-star system, is a lot more complicated, okay, than just Kepler's laws. And we've observed deviations from those Kepler's laws in these multi-star systems, particularly pertaining to the ways by which those planets orbit around that multi-star system. So the issue is the math gets a lot more complicated. It's not that we can't do it, but it's difficult to describe because the systems are not always stable. Okay, the reason our solar system is stable is because we have this one star that pretty much absorbs the center of mass of the solar system, and we have everything orbiting in an ellipse around it. And because it's so simple, the math is very simple, and nature is always just trying to find a balance. And it's simple to find a balance in such a simple system. In a more complicated and dynamic system, it's a little bit more difficult to find that stability and to find that balance. So while they exist, it's not confirmed that they will exist for that much longer. And it's not always that clear how that system will evolve in time, okay? Because often it takes millions, billions of years for these systems to kind of stabilize and find that natural balance that everything is going towards, okay? So to sum up, yes, there are multi-star systems that have planets in orbit around them. However, those planets don't always follow Kepler's laws of planetary motion that we understand for our own solar system. And we don't understand the stability of those systems yet. At least I don't understand the stability of those systems yet. And it's very difficult to mathematically model those systems. But they exist and they are observable. Okay? So since that was a little bit of a long question, I'm going to leave it there for today. But Lillian, I will absolutely be answering the rest of your questions in the next couple of videos. I am psyched that you sent so many questions. And if you think of any other questions, please feel free to send them. That goes for the rest of you too. I hope you're having a really great Monday so far. And I will see you next time. Okay?